LLM analysis results. The provided system description for the Musical Mind Network, MMN, outlines a sophisticated architecture designed to model and generate multidimensional thought, drawing heavily on concepts from neural networks, dynamical systems, and multimodal integration. As an F0Z framework specialist, it is clear that this system, by its very nature, is replete with various forms of circular dependencies, feedback loops, and self-referential aspects, which are critical to its intended functionality and also pose significant challenges. Here is an analysis of the identified circularities. #### analysis of circularities in the Musical Mind Network, MMN. 1. Dynamical state evolution. Internal first-order feedback loop, description, the core of the MMN's dynamic interaction is defined by the recursive update rule for the state vector $math x equals x_h, x_r, x_t, x_d, x_e, $math x_ t plus 1 equals \math x_t plus \delta t \text nn \math x_t \theta $. This mechanism explicitly states that the current multidimensional cognitive state $math x_t directly influences and determines the change that leads to the subsequent state $math x_t plus $1. The system explicitly notes, this system captures feedback loops, such as emotion-boosting harmony or rhythm-modulating texture. Implications this is a fundamental positive feedback loop responsible for the temporal evolution and continuity of the MMN's internal thought process. Stability and instability depending on the function $f, \math x_t, \theta, or the neural network NNS internal dynamics. This loop can lead to stable, coherent trajectories of thought, e.g., a narrative maintaining its flow, or, if unchecked, to oscillatory, chaotic, or runaway states, e.g., thought patterns spiraling out of control or fixating on a single idea. Emergent dynamics complex, nonlinear interactions within this loop are the source of emergent cognitive patterns, such as the blending of emotions with logical flow or the spontaneous generation of novel ideas based on prior states. Temporal coherence this loop is essential for maintaining consistency and progression over time in generated outputs, e.g., text with coherent rhythm and emotion, or music with evolving harmony. F0Z context this is a prime example of a first-order feedback, F1 loop. Modeling in an F0Z context, this feedback loop can be modeled by analyzing the eigenvalues of the Jacobian matrix of the transformation $f$ or $text nn, $s influence on $math x$ around operating points. This helps predict local stability, convergence rates, and the potential for oscillation. Observation the trajectory of the state vector $math x$ over time can be observed to identify attractors, stable thought patterns, limit cycles, recurrent patterns, or chaotic behavior, unpredictable but bounded patterns, which provides insight into the MMN's cognitive style. Leveraging to mitigate the challenge of modeling dynamics over time demands efficient numerical solvers. An F0Z analysis would guide the selection of solvers based on the observed or predicted stability of the system. For instance, if the feedback is highly sensitive, adaptive step-size solvers or robust control strategies could be employed to ensure stable and efficient computation. This loop is crucial for generating continuous, evolving outputs, and careful tuning of its gain parameters within $theta, perhaps via regularization, can prevent divergence. 2. Cross-dimensional attention, interdimensional feedback network, description the system employs cross-attention, $x_i, x_j, where each dimension, $x_h, x_r, x_t, x_d, x_e, can dynamically attend to and influence the others. This creates a fully interconnected network of influences, allowing for dynamic prioritization, e.g., attending more to emotion and rhythm for poetic sentences, or harmony and texture for logical problems. While the formula implies a query-key relationship, the broader multi-head attention mechanism and explicit description of each dimension attends to the others signifies a network of mutual, possibly asymmetric, influences. Implications this attention mechanism creates a dense web of simultaneous feedback loops between heterogeneous dimensions. Dynamic resource allocation it allows the MMN to adaptively allocate cognitive resources or focus across dimensions based on task or context, enhancing flexibility. Synergy and conflict positive feedback between dimensions can create synergistic effects, e.g., rhythm amplifying emotion. Negative feedback could maintain distinctness or resolve conflicts. Miscalibrated feedback could lead to one dimension dominating or suppressing others, reducing representational richness. Robustness and adaptation the ability of dimensions to influence each other provides a level of robustness, allowing the system to compensate for weaker signals in one modality by leveraging stronger signals from another. F0Z context this represents a complex first-order feedback, F1, network, where the attention weights act as dynamic gain controls. It can also exhibit second-order feedback, F2, if the learning process adaptively tunes these attention weights based on the system's performance or internal consistency metrics. Modeling 1 could model the cross-attention mechanism as a dynamic adjacency matrix in a graph, where nodes are dimensions and edge weights are attention scores. F0Z analysis would involve studying the spectral properties of this matrix to understand communication flow, centrality of dimensions, and potential for information bottlenecks or amplification within the network. Observation by visualizing the attention patterns across dimensions during different tasks, one can observe how the system prioritizes and integrates information, revealing its internal, cognitive strategies. This can expose imbalances or unintended strong feedback pathways. Leveraging this feedback mechanism is crucial for mitigating the challenge of aligning heterogeneous data types. By understanding the F0Z characteristics of this interdimensional feedback, one can design loss functions or architectural constraints that promote beneficial cross-attention patterns, ensuring that the alignment is meaningful and robust across modalities. It allows the system to learn how different dimensions should influence each other. 3. Generative output as input. Meta-level self-referential loop / generative autorecursion. Description the MN's ability to produce generative output, text, music decisions, means its internal cognitive state is externalized. Given that the multidimensional input representation explicitly details how inputs for harmony, rhythm, and emotion can be derived from existing music and text, a powerful higher-level loop is possible. MN state $to generate music / text $to re-encode generated music / text as input $to update MN state. This suggests the system could potentially listen to itself or read its own writings. Implications this is a meta-level self-referential loop with profound implications. Self-refinement and creativity this loop could enable the MN to continually refine its internal models and generative capabilities by observing the consequences of its own actions, leading to emergent creativity, self-correction, and potentially even unique artistic styles not explicitly trained on. Mode collapse or divergence without robust control. This loop could lead to mode collapse system generating increasingly similar or degenerate outputs, or an uncontrolled drift, if positive feedback dominates and drives the system away from meaningful outputs. Autonomy and exploration this enables a degree of self-directed exploration of the generative space, allowing the MN to discover novel patterns or relationships through recursive self-interaction. F0Z context this is a powerful, potentially first-order feedback, F1, loop operating at the system boundary, where the system's output becomes its own input. It embodies significant self-referentiality. Modeling this can be modeled as a recursive function $O equals M, I, where $I_T equals O_T1. Analyzing the long-term behavior of this iterative process, e.g., finding fixed points, strange attractors, is crucial for understanding its generative capabilities and stability. One might use concepts from chaotic systems or iterated function systems. Observation by monitoring the quality, diversity, and coherence of outputs over many cycles of self-feedback, one can observe whether the system is improving, degenerating, or exploring new creative territories. Metrics like perplexity, for text, novelty scores, or qualitative human evaluation would be essential. Leveraging this circularity offers a path to achieving advanced forms of unsupervised learning and autonomous creation. An F0Z approach would suggest injecting controlled noise or variations into the re-encoded input to prevent mode collapse and encourage exploration. It can also be leveraged to learn robust isomorphic mappings by forcing the system to reinterpret its own generated outputs, thereby reinforcing consistency between its internal state and external expressions. 4. Training objective and parameter update. Global learning feedback loop. Description the entire training process forms a pervasive feedback loop. The current model parameters, $theta, influence the system's performance, outputs, and internal states. This performance is quantified by a composite loss function $math_L equals $math_L underscore \text task plus \lambda_1 \math_L underscore \text coherence plus \lambda_2 \math_L underscore \text emotion plus \lambda_3 \math_L underscore \text rhythm $. The gradients of this loss function then guide the optimizer to update $theta, which, in turn, alters the system's behavior, closing the loop. Implications this is the primary mechanism for adaptation and learning. Learning and optimization this positive feedback loop, where a reduction in loss leads to parameter adjustments, aiming for further loss reduction, enables the system to learn complex mappings, interdimensional relationships, and generative capabilities from data. Convergence and generalization the stability of this loop determines whether the model successfully converges to a good solution or gets stuck in local minima, oscillates, or diverges. The balance of the $lambda terms impacts how well the system generalizes across different objectives. Bias and overfitting uncontrolled positive feedback, e.g., high learning rates, insufficient regularization, can lead to rapid overfitting, where the model becomes too specialized to the training data and performs poorly on unseen data. F0Z context this is the fundamental first-order feedback, F1 loop underlying all gradient-based learning. It incorporates elements of second-order feedback, F2, when adaptive optimizers, like Atom or meta-learning adjusts learning rates based on the observed rate of change of the loss. Modeling the training process can be modeled as a dynamical system in parameter space, where the gradient vector defines the direction of movement. Analysis of the loss landscape, convexity, saddle points, is critical. Observation training curves, loss over epochs, provide direct observation of this feedback loop's dynamics. Deviations, plateaus, or spikes indicate instability, stagnation, or successful convergence. Leveraging to address challenges such as aligning heterogeneous data types and capturing emotion accurately, the F0Z framework emphasizes tuning the feedback gains, represented by $lambda parameters in the loss function. These parameters directly control the strength of feedback for different objectives. An F0Z informed approach would involve sensitivity analysis of these parameters to ensure balanced learning across all dimensions and prevent one objective from dominating the others, which is crucial for achieving coherent multimodal integration and accurate emotional representation. This loop also allows the system to integrate external sensors by adjusting its internal models to match incoming multimodal signals. Relevant F0Z concepts for circularity.